we defined that this first stage was, let's say, understanding where we start. So basically understanding what is our target. So we could, for example, have a customer target that, okay, we need to ensure that the lifetime of the product under these kind of conditions is 15 years. So basically then it is here, 15 years. Or we have a target coming from the car manufacturer that, okay, the MTTF, so the random failures, you need to have less than 0.1 fix. So 0.1 failures per 1 million operational hours. So that's our reliability target. And now we do some, let's say, preliminary calculations, this reliability methodology at the design table, and we see where we are starting. So this could be failure mode and effect analysis. This could be this mill handbook, MTTF calculations, whatever what we can do in a design day. And then we are having our starting point here, and we know where we target is here, and then we start the testing. And now with the testing, we want to make sure that we, in the end, when we start moving our let's say new design into mass production, then the reliability target has been met. So here the critical stages, which we are mainly talking to through these next 5 or 6 lectures, are DART, design, assessment, reliability testing, and DMT, design maturity testing. And now here today we concentrate on this part, so this DART part, which is basically, if we sum it up, it's find and fix the failures. So I'm coming back to that in a second. What does this really mean? But here we have different tools, and now today we'll concentrate on so-called HALT, highly accelerated live testing. Sorry, there are quite many of these acronyms, but electrical engineering and reliability, they are full of acronyms. So it is good to at least to know what these are. So highly accelerated live testing, this is what we focus today. And then basically we have a identical testing tool, which is called highly accelerated stress test. The idea is the same in both of these, but this utilizes different stresses. And therefore, that's the reason that we are covering this in 2 weeks. So because here we also have humidity included. And now when we made this kind of a definition, or we put a borderline in our lectures, that first we discuss the stresses without humidity and impurity, so then therefore we concentrate on here. But I just want to highlight that HALT testing is also belongs to this DART, design assessment reliability testing part. Okay, so this might sound a little bit confusing and fuzzy, but it will kind of become clear when we go through all these tests, so you understand the purposes. So then it's also much easier to also remember these stupid acronyms which are used. So what is this highly accelerated live testing HALT? So basically the idea is that by whatever means, and whatever means here refers whatever stresses and how high stresses as possible, we try to identify potential failure modes and fix the design. So it means that we again think what could happen, but we are not thinking that, okay, how reasonable these stresses are. So this is another way of putting it, is that HALT is not meant to be a simulation of the real world, but a rapid way to stimulate the failure modes. Meaning that okay, let's have stresses, let's have combination of stresses which really show how high robustness our design has, and if we have any design mistakes. So therefore, as with the single stresses, we would need to go, let's say, insane values, stress values. Then quite often these highly accelerated life tests, they are utilizing combined loading conditions. So this kind of a sequential testing or combined loading. So we will come back on this next week a little bit more detail. So what is, let's say, which kind of relevant combined loading conditions could be utilized, and how we can really utilize the cumulative effect. As you remember, last lecture we discussed about this mill handbook. Was it a table kind of that which showed how the cumulative effects or which kind of cumulative effect some stresses could have. So if the damage from two different stresses can be more than just a simple sum. So if we have vibration loading and very low temperatures, then the vibration together with low temperatures is definitely more harmful, at least for certain materials, than just vibration in room temperature and just low temperature. Like when we have organic material, plastics like that, they become brittle when the temperature goes clearly below zero, and then they are very sensitive on mechanical load. So that is what we are utilizing in this kind of a HALT testing. And the most common combination of stress in HALT testing is that we combine vibration loads as well as temperature cycling or temperature shock. There could be some other combinations. So we could, for example, have temperature cycling and power cycling. We could have some high voltages, high powers together with vibration or temperature or whatever. But from the testing point of view, this is kind of the most straightforward way to combine loads, vibration or mechanical stresses in general, and thermal stresses. So this HALT, let's say, idea or philosophy that has been, let's say, invented by this guy, Greg Hobbs, and they are still on the market selling, for example, the equipment related to this one. They are selling the other tools, analysis tools, and now, of course, we always need to be a little bit careful so that we don't blindly trust what someone who is selling something is telling. So therefore, in this lecture, I also have, let's say, a little bit of critical view also towards HALT testing. I don't say that HALT testing is nonsense, definitely not. It's very useful, but you need to really understand what is your target and how you do it, and how you interpret the results, so that you don't, again, make these, let's say, too quick conclusions just based on what seems to be better than the other one. Or you don't do corrective actions which really do not improve the reliability under field conditions. They are only improving the reliability under these extreme stress conditions. Okay, so let's go forward. So where this HALT testing is typically used, as I already said, it is used typically in the stage gate 2. So it means that we have not yet manufactured the actual products. We are using these tests for breadboards or prototypes, and that means that, for example, the manufacturing methods could be different. So when you go into the mass production, you need to produce, let's say, 1,000 units every day. You need certain tools to be cost efficient. But at the let's say prototype or breadboard case, it is enough that you manufacture 5 pieces of those, and then you can start testing these units. Then the manufacturing method could be something different. So for example, you could use printed wiring boards, which are, let's say, manufactured with slightly different way, because you purchase only a few dozens of those. your soldering methods could be, let's say, more simplified. You can use even manual soldering there just to get all your components on the printed wiring board and something like that. So here at this stage, you don't consider that how relevant, for example, the quality of the solder joint is. You just want to see that, okay, did I do something stupid in the design table? So for example, placing the components on the board is something that you have a huge amount of mass concentrated on certain location, especially if it's in the center of the board. So you can really understand that. Not sure if you see my examples, but basically if you have this would be a printed wiring board, and then it's completely different if you let's say organize or arrange your components evenly on the board when you start vibrating it, or if you have a high mass concentration at the center, because then the mass which is here, if the board would be supported, for example, from the corners, then with the same amount of energy, the board would bend much more if the mass is here rather than it's evenly distributed. So that could kind of indicate you that, okay, now you have your large ceramic capacitors together with your transformers and your main processor, which are all massive components. They are located too close to each other, which means that locally you will end up huge bendings when the board starts to vibrate. And then the point here would be that, okay, we need to do a redesign. Let's move this component somewhere else. Even from the electrical performance point of view, that would not be ideal, but from the reliability point of view, that would really drastically increase the mechanical reliability. So that is the point here in HALT testing. So first of all, what kind of is annoying but need to point out is that even in the name we have this live testing. There's basically nothing which refers to the actual lifetime of the product. So with HALT testing, we do not try to estimate the lifetime or wear out phase, and we do not try to estimate the let's say mean time between failures or mean time to failure. So we don't want any numbers, but we want to find the weakest locations, weakest links in the product as fast as possible. So with supreme time compression. And when we do this, we make our product more robust, so it can withstand higher stresses without failing. That means that most probably we push the bottom of the bathtub curve down, so we decrease the random failures, so we increase the mean time to failure value, and also we push the wear out portion of the bathtub curve far to the right. So we also increase the lifetime of the product, but we don't really know how much. And sometimes it may be that we don't increase, but if the product is more robust, then typically it's also more reliable from the lifetime point of view. So that is kind of the philosophy behind the HALT testing. And now let's go into the, let's say, practical, how do you do the HALT testing? What is the kind of way of doing it? And now I let's say, want to really emphasize that there's, in that sense, no strict rules how you do HALT testing. There is only, let's say, typical way of doing it. And here I have called it conventional HALT, meaning that you use this temperature and vibration together as the loads. And now I'm kind of showing the process, how you end up composing your HALT process if you utilize this kind of a conventional approach. And this then this HALT process is done in 4 stages. And first 2 steps are temperature step stress test and vibration step stress test. Difficult words, but I will explain what do these mean. So how you start is that first you start just testing that how much your product test unit withstands high temperature. So you start from the room temperature, you start going upwards. First you have the 30 degrees or 25, 30 degrees, then you increase the temperature with, let's say, 10 degrees. You use 40, 50, 60, 70, 80, and so on. And the point is that always you need to monitor if the product is functional. So for example, here, when you increase the temperature to 50 degrees, you monitor, okay, let's do an electrical testing that everything is working, good, it's still working. Then you jump to 60, and now you see that, okay, in your testing, something failed. You fix that failure, and you start again. Then you end up seeing another failure in 70 degrees, you fix that failure, and start again. And you do it as long as you cannot anymore fix the failures, or you start seeing wear out mechanisms, so that now this product has been too long time in too high temperature, so it's not anymore overstress failure, it's a wear out failure. The same for low temperatures. So you start again, some temperature, then you go 10 degrees below, you go to 0, you go to -10, -20, and if you find a failure here, you fix it. Let's say you select another component which stands better the cold temperature, you select a new material which is not coming brittle in that temperature or whatever. You come back and do it again. So these are now the temperature step stress tests. And then you have the same with the vibration. So you start with a certain vibration level, increase, find a failure, fix it, and do it again. So basically, you continue these tests, these steps, let's say from temperature point of view, until you have really clearly defined the limits of the sample. So how much the high temperature and low temperature this sample can withstand, or then you end up running out of the capacity of your testing system. So for example, here, now we have this is coming again from the Hobbs company. So they have a specific type of temperature system. So you can go from -100 degrees centigrade up to +200 degrees centigrade. So these are kind of extreme temperatures from the let's say thermal cycling or shock point of view. You need a specific tools, and I will be coming back how you can achieve these very, very low temperatures and very high temperatures. So for the vibration step stress test, then typically you use random vibration or frequency sweep, and you start with certain G levels, and then, for example, here first step would be 5 Gs, and then you do a frequency sweep from 2 Hertz to 2000 to kilohertz, and you do the sweep here. It takes 10 minutes, and you have this kind of a random vibration of frequency sweep with certain amplitude. Then, if nothing happens, then you jump to the next G value, which is here 10 Gs, for example. Do it again, and typically the G values are increased with the steps of 5 Gs or 2 Gs. Really doesn't matter. It's up to your product or which you are deciding. What is basically your guess at how many steps you could see. how the time of the step is determined. So for the, that's a very good question, and basically I have it in the next slide, but I can already say it. So for the temperature thermal step test, it's quite easy to define. It's when you are sure that the temperature distribution, the thermal gradients have evened up. So basically you need to wait as long as you are sure that the whole product or test unit is having the same temperature as your testing ambient. So maybe I will jump back here. Sorry. So like now we are going upwards. We are here, we increase the temperature to 80 degrees centigrade. So now we keep it there as long as we are sure that the whole product is 80 degrees centigrade. So this time is dependent on the thermal mass of your product. If you are testing one single component, let's say 5 millimeters times 5 millimeters times 1 millimeter, this might be only 2 minutes. If you are testing a whole laptop, this could take, let's say, 20 minutes, half an hour, or whatever. So as HALT testing is typically done in let's say, more product level than component level. So typically we need to have quite long time, and it's also how fast you can do the monitoring. So the more complex system you have, of course, it takes more time really to do the monitoring if the product is still working or not. Hopefully you understand what I mean. So if you have a single component, again, it might be quite easy to see that, okay, is it working or not? Let's say ceramic capacitor, you just measure the capacitance value, and okay, it's still okay. It has not, let's say, broken or anything like that. Good. But if you have a full functional unit, a smartwatch, then basically you should be able to test all the functionalities. Is the pressure sensor still working? Is the magnetometer still working? Is the memory component still working? Is the ambient light sensor still working? And so on and so on. So this time is dependent on that. Then let's see, for the vibration, this is, let's say, quite often dependent again on your testing facility. So how fast you can do for example, the vibration sweep. So it would be best if you could constantly monitor the functionality of the product during the whole sweep, but it might be that you cannot do it, so that you would need to do it only that you do the let's say vibration sweep, and then you do the electrical testing. Okay, still working, then you jump to the next, and then you do the vibration sweep. So it depends. Basically, you can do the vibration sweep in few minutes. So it's depending again on your test system. So it does not need to take 10 minutes like here, but that is just the recommendation that to be sure that you see all the possible failures, then you should utilize the functional testing throughout the step, and that would take some time. And now the point was that, okay, now if we find a failure here, we fix it, we come back, we start again, we fix it, we start again, and go like that. So the first purpose of this step stress test is, of course, fix and correct, find and fix the failures, but also to define the limits. And there are two different types of limits which you need to define. First is the operational limit, and then there is the destruction limit. Because based on these these values, you utilize then on the coming two steps. So what does these mean? Maybe a little bit confusing slide, but let's go through it so then it becomes clear. So here we have so-called specification limits. So upper specification limit and lower specification. Maybe it's easier if we think this one as a temperature. So this is what your customer wants. It wants that your product should be operational from -20 up to 80 degrees centigrade. So that's the customer requirement for the specifications. Then you need to, of course, you need to be sure that your product meets those, and you want to have the operational limits. So the upper operational limit should be higher than that upper specification limit, and lower operational limit should be below the lower specification limit, which means that this operational limit means that when you exceed that value, then the product is not functioning anymore correctly, but it is not physically failing. So it means that if this would be then, what did I say, 80 degrees centigrade, then your operational limit would be 100 degrees centigrade. So when you increase the temperature above 100, then let's say the electronics becomes crazy, so that it's not working anymore, but the smoke is not coming out. So when you decrease the temperature then back below the operational limit, then the product starts to operate correctly again. So these operational limits, they are quite often related to, for example, on your component specifications. As you might know, you can purchase the same component with different specifications. So you can have this kind of a commercial grade or consumer grade component, which is specified that okay, it is working between -20 and +80 or something like that. And then you can, for example, have a military grade, the same component basically doing the same functions, but the other one is military grade, meaning that it is operational from -60 up to 125 or something like that. These are just arbitrary numbers. But the point is that the manufacturer of the component have utilized different materials, different designs, so that the component can do its electrical function at lower or higher temperatures. Could there be any other method to perform the test apart from temperature, vibration, for example, voltage or current? Yes. So basically, this is the point here is that now what I'm showing is kind of the standard way, the classical way of doing HALT. And if you put HALT into the Google, you end up HALT chambers, which the companies are selling, and they are most practically always combination of temperature and vibration. But in principle, you can use whatever stressing conditions with the same idea behind. So you could, if you would be testing, let's say again the ceramic capacitor, then most probably your HALT testing could be that you use simultaneously voltage, high voltage, and then temperature. And you start increasing the voltage together with the temperature and see when the breakout comes. So when the capacitor is let's say burning. So it could be as well that it could be high current, as you said. So let's say you have a thin film resistor, and you want to see that how high currents or powers this resistor can withstand at different temperatures. So you would, let's say, use a constant voltage. You start increasing the current, and then you have different temperatures, and again you see that when the thin film resistor just burns. So exactly correct point what you made is that whatever stresses, whatever combinations of stresses could be considered to belong into the HALT testing, but the equipment which is sold, that's there typically it is a combination of temperature and vibration. And this is also definitely the most common way of doing HALT testing, but the others are also possible. Okay, so basically now we defined operational limits, and then quite obvious we have the destruction limit. So if this was 80 degrees centigrade, this is 100 degrees centigrade, then maybe the upper destruction limit could be 120 or 40 degrees centigrade. So that means that we have a permanent failure. If we exceed this value, then the smoke comes out and it is permanently destroyed this product. So even we are decreasing the temperature, it's not, it doesn't become alive again. So that's the destruction limit. So for both for high temperature direction as well as low temperature direction. Of course, for the vibration, we are only going to this higher vibration load. So there's no sense to go lower vibration load. So it's not just leaving it standing still, or you don't have this kind of a negative vibration or whatever. But then you understand the point. And here I have also added these ESS limits. So these are screening limits. So basically, this is something that we come in next lecture or next Thursday, so that we are thinking, okay, how can we utilize these limits, which we have now defined, also for screening purposes. Screening means that finding out these weak units, the weak population. That is really simple thing, and we will cover that one later on. Okay, so now basically what we have done is we can kind of establish the so-called four corners of the HALT testing. What does it mean? It means that here we have the normal production, operational limits, meaning that if your customer wants that your product will be operational within these limits. So minimum temperature, maximum temperature, and maximum vibration. Okay, here again, we have the screening limits. You can forget this gray area here. Then we have the operational limits. So we have the minimum temperature where this product is operating. We have the maximum temperature where the product is operating, and we have the maximum vibration where the product is still operating. So we have these operating limits. And as I said, if we exceed this one, go into this gray area, it's not working anymore correctly, but it is not completely failing. And then we have the destruction limits or the HALT limits. So if we exceed this temperature, if we go below this low temperature, or if we exceed this amount of vibration, then we have a permanent failure. And then the product is dead. And now, based on these values, which we have now defined, we go to these two consecutive steps. And first, or the third step here is so-called rapid thermal stress test. So could also call it as a thermal shock test. So how the limits are there defined and how you kind of do it again in the conventional HALT. So this is just now one way of doing it. You can do it several other ways. You can, for example, define the limits. You can define the number of cycles different ways, still HALT testing. But if you, let's say, obey the classical recipe coming from this Hobbs company, then you do it like this, which I'm now showing here. So in this thermal shock test or rapid thermal stress test, then you do minimum of 5 thermal cycles, so 5 cycles, and how you define what is one cycle. First of all, you want to go on the maximum rate of temperature change. So this is now kind of critical. So you want to go as fast up and as fast as possible down with the temperature. And this is related to now again to the equipment. Which kind of equipment you can have which allows you to go very rapidly up and very rapidly down. It means that you need to have very high heating power as well as you need to have very high cooling power. In a few slides, I'm coming back to this issue, how that is technically possible to do. In principle, you can have even higher rates of temperature change by doing this kind of a liquid to liquid term temperature shock. In military and avionics, there are some standards which utilizes this kind of a testing method. So basically, you have you don't have water, but you have some, let's say, typically, for example, glycerol or some oil, and you have one canister of that oil, which is, let's say, minus 40 degrees or minus 50 degrees centigrade, and then you have another canister which is, let's say, 150 degrees centigrade. And then you have your product, you are just dipping it. First from minus 50, then directly to plus 150. And that's, of course, the most severe temperature change, which typically, let's say, products, normal products, even in automotive or industrial, and definitely not for consumer, the products will never face those kind of extreme temperature changes. So within, let's say, fraction of a second, you change the temperature from minus 50 up to 150. But if you think about, let's say, military, you might have a rocket launcher or something like that, where really the temperature, local temperatures can change when the rocket is launched or something like that. There, the rate of temperature change can be hundreds or thousands of degrees per second or something like that. So that's the reason that there is this kind of extreme way of having temperature shocks. But now we are mainly concentrating on something that you can achieve so that you have your sample standing still, and then you change the ambient temperature. There are some other methods which we let's say look through in next lecture, where you can achieve a little bit higher rates of temperature change without needing to use, let's say, nitrogen cooled chambers like what is needed here. But as I said, I will come back on this, let's say, technical requirements in a minute. But the point was that, okay, as fast as you can, and then how you then select the upper temperature, upper testing temperature and lower testing temperature. And now this is defined from the operational limits. So you are within 10 degrees of the lower and upper thermal operational limit. So as an example, if your operational limits which you defined in the step stress test were minus 50 and plus 100, then your thermal stress test would be from minus 40 up to 90. And minimum dwell time will be 5 minutes. So that is again dependent on the stabilization of temperature in your product. So what does this mean? I think this is more easier to see here. So upper operational limit, you take 10 degrees off. Lower operational limit, you take 10 degrees off. So this defines the maximum temperature in the test and the minimum temperature in the test. And then you do it as fast as possible. And then you keep it there, minimum of 5 minutes, but it is dependent again on the thermal mass of your product. So larger the product is, the longer you need to do. And again, why you need to be in operational limits? Because you want to monitor the product during the whole cycle, all 5 cycles. So minimum of 5 cycles with these kind of parameters and constant monitoring. That's recommended. If you cannot do it, then you should do the monitoring at least here and here. Then finally, the 4th step is you combine the vibration together with this kind of a temperature cycling or temperature shock. I would really like to call this shock because you want to target on as fast as possible. So how you then define the steps into the vibration. So now instead of operational limits, you take the destruction limit, which you defined in the vibration step test, and then you divide that one by 5. And every cycle you increase 1/5 or 20% of the vibrational loading. So you use the same frequency sweep or random vibration with a certain G value, and you increase it every step. So if I think this is obvious, but if you have, for example, that the destruction level of your product, which you could achieve in the vibration step test, was 35 Gs, then you divide that one by 5, you end up to 7. So you start from the first cycle, you use 7 Gs, then for the next one, it's 14, 21, 28, and then finally 35. If your destruction limit was not defined, then you just use the maximum value which you obtained there. You can, of course, use some other. It's always said here that, okay, this is just a basic recipe. You can do whatever you want. You can do more than 5 cycles. You can start with the higher or lower vibration levels, whatever is what you want. But this is the typical way of doing it. And again, here you target to at least 5 combined cycles. So now if we merge these together, so here we have this is the operational limit for the temperature, and this dashed line also refers to the destruction limit for the vibration. So first the thermal cycle, 10 degrees below operational limit, upper operational limit, and 10 degrees above lower operational limit, and 20% from the maximum G value in random vibration. And then the second cycle, you increase the vibration into 40%, 60%, 80%, and then 100%. So you can understand that this now is an extreme testing. So basically you have your product, you are simultaneously shaking it to all directions, and you also go temperature upwards and upwards and upwards, and or cyclic upwards and downwards, and so on. So it means that if your product can withstand this, it will become quite robust. So it's easy with this kind of a way to find out the weakest links. What would fail? And then the question is, are these failures relevant or not? There's other ways which you can do. So you can simultaneously increase the vibration loading as well as the delta T in your thermal shock, like this. So what is shown here, this is again the classical recipe, but you can do whatever way. And the idea would be that you could monitor the product throughout the whole period. But sometimes that is not possible. Then you need to monitor at least here, 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 here at the end of each cycle. So like here. So this is something where you see that the temperatures are here. This is the vibration. And then here you can see where the power in the product is on and when it's off. So when the power is on, then you can do the functional testing. So here, basically the idea would be that you do when you have reached the temperature, upper temperature, and the vibration is on, then you do the measurement, then you keep it there for a certain amount of time, you do a measurement again, then you go down to the temperature, you do the measuring or operational measuring, so functional test, and again. The problem with this kind of approach is that quite often the failures are visible only here. When the temperature is changing, you get these thermal gradients, meaning that certain parts of your product are cooler, certain parts are warmer, which let's say increase the stresses locally, together with combined effect of this vibration loading, together with thermal gradients, and there you might have this kind of a let's say problems which are coming, for example, electronic connectors, so which the electrical connection is based on the mechanical contact. And then, let's say, temporarily, the mechanical contact could be decreased because of the combined effect of vibration and thermal distribution, and then your contact resistance is increased. And then you see the problem only here or here, but you are not seeing it when the temperature has stabilized. Therefore, it is strongly recommended that you do the functional testing throughout the whole cycle, but that is not always possible. So it's again dependent on your measuring system, on your device, and so on. So kind of as a conclusion, so what are the basic steps in HALT? So now these are basically different steps what we just talked. So first we have this precipitation. So we use different types of stresses. Then we try to detect what is the failure. First, if we have a failure, then what is the failure? And then we analyze the failure so that we can correct the failure. And then we redo the test and see that our corrective action was correct. And then we document it. So we run this loop again and again and again. And then we can, let's say, be sure that our product is robust enough. But we need to remember that most of the failures, or at least large fraction of the failures, are not hard failures. Meaning that, again, this hard failure means that something is permanently destroyed. It might be that because of this combined temperature vibration loading, we have temporary failures, so-called soft failures. So something is temporarily out of order, like this previous example that we have a mechanical connector, electromechanical connector. So this contact interface is just during the ramp up or ramp down, it's not in proper contact, so the local resistance is high. So then the system, for example, if this is a power connector, it kind of loses the power, but it's not something that permanently fails. So that's the reason that we should always, if possible, monitor during the simulation all the time, if it's possible. So then you would really see what are these hard failures, permanent failures, what is really the situation where the failure occurred, and then you can do, let's say, corrective actions. Okay, so again, this is coming, now we jump a little bit on the what kind of equipment you would need. And first slides were, let's say, the idea behind. And now what you really need to have if you want to do this, according to this, let's say, classical recipe which describes. So basically, these are now the chambers which this company is selling. And now, again, I don't have any relations to this company. And as you will see, I'm trying to show the positive things here, but also the drawbacks. So these smallest chambers, these are, let's say, size of larger than microwave oven, but maybe a little bit smaller than standard refrigerator, but maybe closer to refrigerator. So the chamber size is something like maybe half a meter times half a meter times half a meter, whatever. So you can fit that type of or size of products inside. And the largest ones, I'm not sure if this is the largest one. It used to be a few years ago, but they could have even larger. So these are the actual testing volume could be several cubic meters. So maybe not, you cannot drive a whole, let's say, Fiat 500 there inside, but quite close to that. So I know that there are several, let's say, industrial electronic companies in Finland who are having these kind of testing facilities, and they are utilizing them heavily. So, for example, maybe not talk about names, but at least a few years back when I visited the company, which is one of the largest elevator or lift companies in the world, they are testing their parts from the elevator systems in this kind of an HALT testing machine, which really can fit very large product inside. Okay, so that's just what is basically available. If you have the money, then you can go to the shop and purchase these kind of devices. What they claim is the good thing with these kind of chambers is that the typical mistake, which is frequently done, is to try to use single axis electrodynamic or mechanical or hydraulic shakers with mechanical refrigeration thermal systems. Okay, maybe it does not tell anything to you, but what this means is that they have a specific type of tool which you can do the vibration loading, random vibration, instead of having just make a shaker which would allow the vibration load for one single dimension. And on the other hand, mechanical refrigeration here means that you have a similar type of cooling system that you have in your freezer. So you have a compressor there which kind of produces the cold ambient. And that of course has its limitations, and typically the limitation is there around -50, maybe -60 degrees centigrade. But with this kind of a mechanical refrigerator, you cannot go to -100 degrees centigrade. So that is kind of that they claim that, okay, you cannot use this. So why? If you cannot excite all the possible failure modes, then probably you will miss those which will be important for you. And okay, so I put both these in quotes because this is what they are claiming, and now we could kind of think of, okay, is it always necessary to have this kind of equipment which they are selling? So basically, now a short discussion, what is the difference between mechanical refrigeration and liquid nitrogen cooling? So if you have liquid nitrogen cooling, then basically you can go to lower temperatures. Like I said, -100 degrees centigrade is not a problem with liquid nitrogen, as the liquid nitrogen temperature is, if I recall correctly, is -197 degrees centigrade. So you can go to low temperatures and you can have much faster rates going downwards. Of course, heating is not a problem. It's just a question of electrical power. So you put more power, electrical power, then you can heat whatever mass to how rapidly you want. So that is just a question of electrical power, how large cables you need and what kind of resistors you have in your system. But the problem is that the low temperature and cooling rate. And now with the liquid nitrogen, you can have faster cooling rate and colder temperatures. But the problem there is that the installation cost is quite huge. So liquid nitrogen is not coming that easily to your test chamber. So for example, those who have visited Micronova, you see that in the backyard, in the close to the car park or parking place, there is a large liquid nitrogen vessel, which AGA, the gas company, is filling every week. So the tank car is driving there every Friday and filling up that liquid nitrogen tank. So you need to have that kind of tank, and you need to have the liquid nitrogen available. And that is a huge cost difference between that kind of an infrastructure versus that you have just a compressor. So this kind of an equipment which uses compressors or standard mechanical refrigeration, the cost is less than 100,000 euros, clearly less. But if you need to have this kind of a liquid nitrogen infrastructure, you can easily spend 1 million euros just to build up the system, and then the operational cost is also there. And the other thing is that so you need to have the installation money, and you need to have the operational, and you need to have also competent personnel to operate these kind of liquid nitrogen related systems. So that is kind of what the first decision what you need to do if you would go on to these kind of chambers utilizing liquid nitrogen, or could you use just a normal let's say thermal chambers which uses mechanical refrigeration, and then you are limited with the temperatures, lower temperatures and rate of temperature change. Then about the vibration, so this these equipment, which is again produced by this HOPS company, they are offering you so-called 6 degrees of freedom by random vibration. It means that if here you have your vibration table, this is your product, which is you are testing, then this vibration table can move in X direction, Y direction, Z direction, as well as have rotation along X direction, so alpha, rotation along Y direction, and rotation along Z direction. Meaning that you can shake it whatever direction, and you can also simultaneously rotate. So basically, you can have acceleration and rotational forces to whatever direction you want to have. And they claim that that's why it's better than this kind of let's say single axis vibration. So typical vibration shakers are such that instead of having this kind of a system, you have just a shaft which you electromagnetically move upwards and downwards. So basically you can only have Z-axis vibration. That is much more easy to control because you just need a signal generator and amplifier, and then you just move the table upwards and downwards. But of course, if you want to check X, Y, and Z directions, then you need to do it 3 times. You need to flip your sample, and you cannot have these rotational forces. So there is now advantages and disadvantages. The other advantage is that with this kind of a let's say electromagnetic shaker, for example, you can easily control your vibration. So for example, having sinusoidal vibration load, where you can really just based on the let's say sinusoidal wave, you just have second derivative, and then you get the G values. So how rapidly the G is changing, or the forces are changing. But if you want to have this kind of a 6 degrees of freedom, then you use this kind of pneumatic hammer. So basically, with a pressurized air, these pneumatic hammers are hitting this table, where then you can have all these different directions of forces, and then in the random vibration, you cannot directly measure the G's, but you need to measure the root mean square G square. So it's a so-called power spectral density, which you measure in random vibration. So that is the basic difference. And what is let's say a drawback on these is that these pneumatic hammers, you cannot produce very even power spectral density with very low frequency. So if you want to go a frequency of 1 hertz, so basically 1 cycle per 1 second, then these are not capable of having very high G values on those. So that is very simple, easy to have with a vibration shaker, electromagnetic vibration shaker, but not with this kind of pneumatic hammers. But on the other hand, you cannot have all these different directions simultaneously. So these are basically the differences. And now we could kind of conclude that, okay, what have we learned from the basic HALT process. So what is the idea? And then also what kind of tools you need. So first of all, HALT is a simulation test. So the purpose is to stress the product until the failure, and you don't consider that much the relevance of those stresses. So you can overstress. You can use stresses or combinations of stresses which the product would never see in their real operational life. That is not the point. You don't simulate the world, but you stimulate the failures. The other thing is that the stress state during HALT process is very complex. You can think that, okay, something fails, but it is really difficult to know what was the actual stress condition. So in which direction, which acceleration the product was moving, and what temperature when the actual failure occurred. And this is especially true because you cannot constantly monitor all the functionalities. The more complex your system becomes. So, because everything is changed in a fraction of seconds, these movement directions, the temperatures, and if you need to do constant electrical monitoring, then you really don't, you may not know that, okay, this was the exact stress condition when something fails, so how can you do the actual corrective action? So, basically, we don't use, HALT is not intended for lifetime calculations. So we shouldn't use HALT for estimating lifetime, but if you Google it, you see at least certain amount of papers which are claiming that, okay, we did HALT testing and we verified the reliability of our product. And this is based on, let's say, using different types of tests, accelerated tests and highly accelerated tests to normal use conditions, and try to understand the acceleration factor between those. So maybe this is a little bit difficult to understand, but if we have here our use conditions, so these are, let's say, the normal operating conditions. These are the accelerated life testing conditions, which we are coming to next week. So let's say that here we use relevant stresses, accelerated stresses, but relevant levels. And we know the correlation, the acceleration factor, that if in use conditions, this product, the lifetime is 10 years, in HALT testing, we need to use 1 year of testing time so that our acceleration factor is 10. And then if we do the HALT testing and we do the testing instead of 1 year, we do it in 1 month. That's not a good example for HALT testing. We should do it in 1 day. Then basically we have an acceleration factor of 2, which is 360. So now if the failure mechanisms are identical, meaning that the slopes of these curves are identical, so that the viable beta parameter is identical, then we could basically calculate the use lifetime based on the HALT results if we just sum up these acceleration factors. So here, in fact, multiply. So basically, here was an acceleration factor of 10, and here was an acceleration factor of 360. So we have 3,600 is the acceleration factor from HALT testing to use conditions. And now this already should, okay, ring a bell that can we accelerate so much that we can simulate 10 years reliability in 1 day? And typical answer is no, but in some cases, maybe. Quite often it is like this. So in the test conditions, you end up having different failure mechanisms. So your slope is different. So depending on which points you take, you have completely different acceleration factors. So this just means that if the slopes are different, you have different mechanisms. No way, you cannot define the field lifetime based on the test lifetime. So what the HALT is good for, and I'm stopping in a minute. So it's design a tool, it can be used, for example, to compare different designs. You have this different, should I put this component here or there? Should I use this connector or that connector? Should I use the component from this vendor or the material from that vendor and compare it? So you can clearly see that which is better than the other, but you don't see how relevant this is. And then these NTFs or NFFs, so meaning that no trouble found or no failure found. So field return, which you can define as what is wrong, then you can use HALT testing really to bring up the problem. You can check the changes, the effect of changes. If you change something, you take a new manufacturing process, you take a new component, new material, then you can see that, okay, how that affects. And let's say the successful HALT testing in prototype level does not always assure that you have nice results in the volume production, because you do these devices which you use in the testing can be manufactured in a different way. So the quality of, for example, in the connections might be different. So to sum up, there's no general HALT profile or procedure. There is just a philosophy, HALT philosophy. So you can use whatever stresses, whatever combination of stresses to figure out the weakest links and then try to improve the robustness of your product. Okay, so basically this is the final slide. So to stimulate the failures, but not to simulate the failures. And we don't have any, let's say, universal standards how you should do it. We only have the, let's say, the recipes which are coming from the companies who are providing this kind of tools.